still not tired of this. Even when the pills you take turn you to a ghost, you still spin around the most. Because I am a member of the butterfly culture, where we work and we take, we play and we pray to God that the girl in that dress will undress and distress you with the way that she moves. I am a member of the butterfly culture, where we work and we take, we play and we pray to God that the girl in that dress will undress and distress you with the way that she moves.
Ladies and gentlemen, please welcome Mike Heil, President and Chief Executive Officer of the Ohio Aerospace Institute and General Chair of AIAA Propulsion and Energy 2014.
Good morning, everyone. How's the conference going? What do you think? Has it been going well? Good event? Great, great. Thank you, thank you. Well, we're on day 3 now, and so I think the first 2 days have been absolutely outstanding. I've been out looking at the technical sessions, at the Forum 360 sections, and then, of course, the plenary sessions, and what a tremendous group of sessions, what a tremendous crowd we have here. Great connections, great knowledge to be gained, and I mean, what a wonderful day yesterday. You know, I've been coming to these kind of events for a long time now, and for the first time ever, I had a plenary forum speaker talk about warp drive at a propulsion conference. So I thought that was absolutely outstanding to have people thinking at the far, far future. Hopefully you've had a chance to get out and see a little bit of the city of Cleveland and take a look at the neighborhood here while you've been here in Cleveland for this conference. So again, thank you for attending. On behalf of the Executive Steering Committee and everyone who helped plan this event, I'd like to welcome you here for day 3. And we look forward to a really great day today as well. Once again, I'd like to thank all the planners. I'd like to thank my fellow planning committee members and chairs, Integration Chair David Eames, Technical Chair George Williams. But in particular today, I'd like to thank the AIAA staff. Kathy, Craig, and everyone else who does all the work behind the scenes to make events like this a big success. So how about a round of applause for our AIAA staff? So, you know, the first day we took a heavy emphasis on propulsion. Second day, a heavy emphasis on energy and advanced energy and the synergy between propulsion and advanced energy. Plenary sessions have emphasized this. The Forum 360 program presentations have emphasized the synergies. Today, we are going to take a look at a very, very important area, which is advanced manufacturing and additive manufacturing. I would add that any of the plenary sessions and many of the Forum 360 panels, we are recording these sessions, and they will be accessible on the AIAA website in coming days. Also, this event would not be able to be put on without the support of our sponsors. So I'm going to mention them once again. Executive sponsors, General Electric, Lockheed Martin Corporation, and NASA. And then our additional sponsors, Dunmore Corporation, Jacobs, the Ohio Aerospace Institute, Sierra Lobo, Southwest Research Institute, United Launch Alliance, IEEE and INCOSI, and also our media sponsor, Space News. So how about a round of applause for all of our sponsors who help make this event a success. We're going to have a great presentation this morning. At the end, we're going to have a question and answer session. So I ask, when you ask a question, go to one of the microphones that's set up in the room. So without further ado, let's go ahead and get started. I'm very honored to introduce our plenary speaker this morning, Mr. Greg Morris from General Electric Aviation in Evendale, head of additive strategy and business development manager for GE Aviation. His biography is available on the forum's webpage, but Greg and General Electric are really adopting and getting ahead of the curve on this important new technology of additive manufacturing, which could be a paradigm shift, a game changer. How many other buzzwords can I use in our business of aerospace, and particularly aerospace propulsion and energy? So please welcome Mr. Greg Morris.
Thank you. All right, thank you, Mike. Good morning, everybody. Good to be up here in Cleveland. It's not football season, so I'm allowed up here. Decided to keep my stripes back at home. All right, so want to go through a presentation. I'm going to cover broadly additive, and I will get into a couple of case studies and examples of how GE is using additive manufacturing. One of the things you'll notice in my presentation is I will tend to talk a little more toward the metals, but I will cover some of the polymer as well. But first of all, let me give you a little bit of history about who I am and where I came from. So originally, I've grown up in Cincinnati, and I came back and started in a family business that was in the steel distribution industry. So we ended up selling that business in the early 90s, and my brother and a partner, a friend of ours, created another company called Morris Technologies in 1994. Now, Morris Technologies got involved in the rapid prototyping industry, and our first machine was an SLA 250 machine. So that was a machine produced by 3D Systems. And it was a polymer-based machine with lasers, 3D CAD polymers. And at that period of time, back in the early 90s, it's important to remember that CAD was just coming out. 3D CAD was just starting to make its presence into industry. The web was relatively new. Email was relatively new. So a lot has transpired in the 20 years since. And certainly the technology has come a long way. But we first started with one machine and ourselves and no customers and opened the doors. One of our first customers we called was actually GE Aviation. They were local, and of course there were some other local companies in the medical field, the consumer products field. So we started in business. We offered engineering design services. We kept reinvesting back in the company into rapid prototyping equipment. We got involved in other things beyond additive. We started to add to our capabilities with subtractive capability, machining basically. In 2003, the game changed for us when we invested in a technology called direct metal laser sintering. We were the first North American company to introduce this technology, and it's a technology that was produced by, and still is, by a company based out of Munich, Germany called EOS. So we took a big risk. We saw this technology. We said, this is, I actually saw some mold inserts at one of our customers, and I thought, wow, this is a great technology to make really detailed, fast mold inserts for plastic injection molding. That's one of the prime reasons why we ended up acquiring the technology and bringing it over. So we did that, and we thought we'll have 75–80% of our business in this new mold-making capability and this tooling capability with this machine, and we'll probably make a few parts here and there. So that just gives you a preview of, we didn't have this all planned out for sure, because the complete opposite happened. Our customers really gravitated toward wanting to have direct parts, not mold inserts. And to this day, that continues to be sort of the trend in North America. So most of our customer base was consumed in the aerospace industry as well as the medical industry. We did have some consumer goods, energy, DoD, oil and gas, but ultimately, before the acquisition by GE Aviation, we were about 135 employees. We had two companies, Morris Technologies, and we had set up in 2007 a sister company that was aimed at production using additive metals. So that was really kind of the first company to say we're going to take this technology, put it into the production arena. And we were able to do that, and I'll get into this because we found confidence in the technology. But on November of 2012, GE Aviation acquired both of our companies, and we rebranded ourselves. So now what was Morris Technologies, we now call our Additive Development Center. And the mission remains the same. We have prototyping, R&D activities, and then RQM has been rebranded our Lean Lab. GE has a series of Lean Labs, and that's the industrialization and productionization of the process. So it's basically taking the process or any technology, any of our advanced manufacturing technologies, and moving it from R&D, starting to scale, and basically handing it off to a production facility. So how we look at our progress or how we look at advancing technology through the corporation. We're very lucky that we have the Global Research Center. They have multiple sites around the world. We deal quite a bit with Niskayuna, New York, and what they do is a lot of TRL and MRL levels 1 through 3. In the additive space, that's where they sit, and then the Additive Development Center for Aviation really looks at those TRL, MRLs, probably about 3 to somewhere around 6 or 7. And then our Additive Lean Lab takes it up right before production, TRL 9, and hands off at that point to our production site. So we have, of course, the GRC, we have the ADC, we have the ALL, we have our cousins in Italy that are very focused, a portion of their business is focused on additive and electron beam melting in particular. And then just a couple of weeks ago at the Farnborough Air Show, we formally announced where our first production site is, and that's going to be down in Auburn, Alabama. So that is where we will produce our field nozzle, which I will also talk about here in just a minute. So look, GE Aviation is clearly, I think, has been leading the charge relative to additive internal to the larger corporation. But as everybody probably knows, GE is a large industrial conglomerate. So we have businesses in power and water, we have healthcare, oil and gas, transportation, appliances, and all of these businesses are starting to leverage and use additive technologies. That can be additive metals, it can be polymers, and it can be other type of materials. But the point is, all of our businesses have really started to leverage this technology in a variety of very interesting ways. Now, some are using the technology more for the prototyping part and phase of the process. But I will tell you that folks like power and water, oil and gas, and aviation, of course, have not only leveraged and used it for some prototyping and tooling and fixturing, but we clearly are taking the technology into a whole nother realm, which is production and direct production of components using additive. And in our case, the first parts we'll have on our engines will be additive metal components. So look, I don't want to make an assumption about everybody's understanding and familiarity with additive. So let me just kind of, if you'll, for those who are familiar, just give me a few minutes to go through this. But really, the technology works in this way. We take a 3D CAD model from the engineer or from the designer. We slice that into very thin layers. And then we orient that, we add support structures where needed. We probably modify it in the case of metals in order to add stock for post-machining, those type of steps. We then download that to the machine, whether it's a laser-based machine or whether that's an electron beam-based machine, and the machine will build that part. And once that part has been completed and built, we then pull it out of the machine. We typically go through a post-thermal processing, so a stress-relieving operation, typically HIP, solution heat treat, that type of thing. Once it's through on the thermal processing, we then pull the parts back. We typically, again, will have some kind of post-machining in order to have a good fit-up capability and tolerances in certain areas. We might hand bench the parts to get a better surface finish. Then we inspect, and then we can ship the parts. So depending on the complexity of the parts can be large, they can be small, they can be complex, typically complex and typically small right now given the state of the industry. But once that's done, we're able to ship parts within perhaps a couple days up to, say, a couple of weeks. And I'll go through a few examples where the timelines are a little bit longer depending on what the project was. All right, so if we can go ahead and roll the first video here. What I want to show you on this video is in essence, the electron beam process. So no sound on this, so you get to hear me drone on through this video. But so we're going to take an example. Of course, we're aviation, so and I'm borrowing this from Oak Ridge. They didn't do this for us, but I'll take this example of a turbine blade. So if you take a model of a turbine blade, we slice that part up into thin layers, and you can see that's being done on CAD right now. That part is then downloaded to the machine. Now, the way the electron beam technology works is it goes into a chamber where you have those buckets that are coming out. We fill those, let's say, with titanium in this case. So we fill up the material dispense areas. We close the door. The electron beam works under vacuum. So then we pull vacuum. That helps us on elimination of oxygen, et cetera. And then the first layer gets swept over, and we preheat every layer. That's one of the uniqueness about the electron beam technology. You can preheat each layer and then precisely come down and melt in the X and Y, the layer or the area you want to form. That process repeats itself. Now, the preheat allows us to work with some alloys that would be crack alloys and things that we would not necessarily easily be able to work with on the laser-based processes. Of course, we can work with titanium, Ti-64, and laser as is in EBM, but in some geometries, it's faster in the EBM process. So once the part's done, because we preheat every layer, one of the problems we have is that it comes out, it's not a problem, it's just an obstacle here, it comes out in a brick because the material that wasn't fully melted needs to then be blasted away, and we use the parent material to do that. So as you can see, once that brick has been removed and that goes back to powder form, you're left with your solid part as a three-dimensional component. So the beauty of that is we can, again, with the RCAM and EBM technology, we can build things very quickly. We're dealing with 3,500 watts of power. It's being directed much like a TV cathode, so it can jump the beam very quickly. You contrast that to the laser, and the laser has 200 to 400 watt typically as power in their machines. And there are pros and cons to each technology. So I will tell you that not one technology, in my opinion, is the winning technology, if you will. I think they have their areas and their niche that they should play in. So I just simply use that video because I have one that illustrates the general process of additive and slicing files, et cetera. All right, so let's talk a little bit about some of the different types of additives. So on the polymer side, this is not comprehensive at all, but the well-known technologies are the one that sort of started a lot of things out in 1987 timeframe, which is stereolithography, or SLA. That was created by a company called 3D Systems and a gentleman named Chuck Hull. Other technologies have come from that. So we have the fused deposition modeling, we have selective laser sintering, we have the polyjet technology. So all of these are polymer oriented. The materials that you typically see will be like plastic injection mold materials. So you'll get ABS-like or polycarbonate-like. We can in the FDM, we can do ULTEM. And in fact, in the Additive Development Center at GE, we have the ULTEM material, we have the fused deposition modeling. We actually have all of those technologies except for the selective laser sintering. And our appliance cousins has the SLS technology. So the beautiful part about these technologies is we went from an industry where the first and early days, when we first had our SLAs, we would produce these components, and if you dropped them from a few inches off the table, they would shatter. They were very brittle. The material properties were not very good at all. Still revolutionary technology to be able to hold a complex part in your hand, but nowhere near where we are today. The materials that we have today are highly functional. So we see people using these materials in a variety of applications. And the plastics and how we use them within GE Aviation, we use it for a lot of fixturing. We do use it for some early tooling. So some of our advanced technology, like our CMCs, we can use it to make early tooling. It's not as accurate as, say, the final machined steel tooling, but it does make it through enough of the process that we can get early looks. You know, there's also other technologies that are coming out, a ton of them. So I'm not trying to be comprehensive in this presentation at all, but nano is another area that's very big. So it's hard to see the scale here, but that horse head, that little line on the neck of the horse, that's 2 microns, that line. So you can see that nano additive is another technology that some industries have quite a bit of interest in. The medical industry is a good example. We also see other technologies where we can print in color. So no, that's not a real orange, and it's kind of a spooky face. But basically what happens in this technology, it's paper-based. So produced by a company called MCOR. So you can take normal 8.5 by 11 sheets of paper. They bond one layer to the next with a glue, and they have a little knife that comes around and cuts the profile of that layer. It also cubes the rest of it, and then you pull the cubes away after your build. But you can print in color. So that gives you some capability. Now, we don't use this technology in aviation, but you can see where if you were trying to do a 3-dimensional representation of an FEA model or something, this is a pretty inexpensive way to go. And so technologies like this exist as well. On the metals front, and this is where I will spend more of the presentation time and where we see more of the applications within GE. So the metals are very broad. I'll get into more of the machines, but you can see the type of applications. And most importantly, if you look in the middle picture and you see that organic bird bone-like structure component, that's the kind of thing our engineers and our designers are starting to look at more and more. It's not how I've designed and created things in a traditional manufacturing methodology. We need to think about how does nature want to potentially drive the design and drive the mechanics of what that part should look like. So in the case of the middle part, you can imagine if that had been a solid part with tubes coming in one side and maybe it was a casting before, if we can still get the same mechanical properties out of that part, but we reduce the weight by 50% or more, we have a substantial benefit. And of course, on any kind of flying hardware, whether it's going up in space, whether it's going to a commercial or military application, weight and fuel savings is a tremendous opportunity, and that's something that we're actively looking at. There's other pictures up here, some unusual designs around heat exchangers. You can see a tooling example where you have conformal cooling. So for those who do get involved in any kind of tooling, whether it be for plastic injection or other, you can see where that could be very beneficial to reduce your cycle times. So when we talk about metals only, this is something I think that is important to understand. When we first brought the technology of direct metal laser sintering over to North America in 2003, this chart would have had maybe a couple of boxes on it. This chart now has a number of boxes, a number of modalities. So we have direct and we have indirect to metal. We have in the direct a number of different capability beyond just laser base. We have laser base, we have EBM base, we have powder bed, we have powder fed or powder injection, we have wire fed. So there are a number of different metal, just metal additive modalities. So one of the important things I think to understand is that no one technology, no one manufacturer or OEM of these technologies will probably fit the full spectrum of parts that you might want to make in metal. So it's really very important to understand the nuances, the pros, the cons of each of these. And by and large, I think what you will see, broad brush, is the powder bed laser-based technologies are more prevalent by far as an installed base in the world. I think you will find a growing number of the electron beam in different forms starting to come out. And I think you will start to see some of the hybrid machines and some of the laser-fed or powder-blown type of technologies increase in popularity, mainly because you can do larger structures. You can do near-net shaped parts with those. So, great technology. We look at it as being disruptive. We look at it as being very enabling. But I will tell you that design matters a great deal, and I touched on this before. But, let me give you an example. So, on the left, what you're looking at is a traditional, what we call panel-style rake. That's an instrumentation probe that we put into our test engines. So that rake takes data. It collects data such as temperature or pressure or emissions. So what you see is the completed rake, and then you see a cutaway of what's inside of that rake. It's called a panel-style. You see little panels in there, et cetera. That's not a traditionally manufactured one. That's actually additively produced. But it was designed to be traditionally manufactured. It was designed to be tubes bent, sheet metal bent and folded and welded, fabricated basically, So it was really a multiple of parts coming together that were fabrications to create this rake. So back in 2005, we were approached by one of the engineers in our test facilities engineering area, giving us this file and saying, can you build this part? We said, sure, we'll give it a shot. So we tried, and the machine promptly crashed on us. So we restarted, did some tweaks, and restarted another build, and that crashed. So I'll save you all the multiples, but it came down to about 11 or 12 tries before we finally got this thing to build, and a lot of little tweaks to the design. So, you know, we quickly realized this isn't the way to go, is to have to keep rebuilding parts like this. So that's when we got a little smarter, and we said, you know, I think what we need to do is just throw this traditional design component out the door, and let's rethink this. Let's rethink what this should look like to meet all of the functionality that the engineers and the designers wanted, but yet be able to grow this without having a bunch of build crashes and costing us huge sums of money. And that's what the on the right-hand side, that's what you see, is a redesigned rake. And this has been very, very successful. So we have all the functionality. In fact, we have even a better rake. It costs less. We have fewer rakes we have to make because it lasts longer in the test. We have better cooling of the skin. And we put all this complexity into the rake and have a very sophisticated piece of equipment that we can grow first-time yield. And it's a very interesting path and a very good story about how you just can't generally take a traditionally designed component or assembly and expect that you can just additively produce it. You will probably need to design around some things. So we fast forward, you know, taking some of that concept of designing differently. Some of you may have been aware that probably about 6 months, 9 months ago or so, maybe it's been a year, GE went out and did a design innovation quest, basically, and we went out to the world and said, okay, here's one of our brackets that we use, and you can see that it has a little GrabCAD logo over it. Here's a bracket that we have in aviation today. It's kind of chunky and big, and here are all the constraints that we're going to put around it. So we went out to the world and we said, can you, the world, those who are signing up on GrabCAD to look at this, can you come back with this design challenge and give us your design that you think is going to be lighter, but yet still meets all of the mechanical requirements of that particular bracket? So we had actually over 680, probably closer to 700 entries that came back. And we took the top 10, and then we actually produced and grew the designs that came back. And you can see some of those. They really are very creative. Some of these are engineers. Some of these were non-engineers. These are people coming from all different industries. They were not just aerospace. In fact, the majority were not aerospace. So what we had is a community of people globally coming back and saying, okay, great. Yeah, I can take that bracket and I can take a lot of weight out. In fact, what we saw is that we saw roughly about an 85% reduction in the weight of that bracket as at how it was traditionally designed at aviation. And applying additive concepts, we were able to reduce the weight and keep all of the mechanical properties. So, you know, I don't think I'd be here talking, and I don't think we'd have all the things I just previously showed you if it weren't for the materials that we use and the great properties that we're getting out of these materials. So I'm going to make a very broad brush statement, and this is dangerous, but I'll do it anyway. So the materials typically that we see coming out of the machines are wrought-like in their properties. So I'll have a few slides following here, which I'll show you. But they're wrought-like in their properties, which gives us a huge amount of flexibility. So all of those parts that have been castings, we feel very confident, with the exception of maybe very, very high-end, like single crystal castings. But most castings, we feel very confident we can take this technology and apply it to those type of parts, and in fact, make them more efficient, make them better. Now, the parts are the alloys that you see on the screens here. So some of those, many of those we use in our laser-based process, and then a few of those we're using in our EBM process. And the light gray shaded ones are the ones that are in the EBM process, so that would be our Ti-64, our cobalt chromium, and then our Avio cousins have had a tremendous amount of success working with Ti-aluminide. And that's a very difficult alloy to produce in the laser-based process. Now, in the laser-based process, we have all of those, except for the thialuminide, we have all of those alloys up there that we've either experimented with or have qualified. In aviation, as many of you would expect, it's a lengthy and a costly process to develop your material curves. So we really only have a few that have been fully characterized and that we have our curves on. However, there are a number of alloys that we work with in prototyping, which are perfectly fine, and then we have others that are not up here that are in development, and I'm aware that a lot of work is being done at the universities, industry, and the government on some other alloys that would be quite interesting. So let's take a look at a couple of these alloys. So this one happens to be cobalt chromium, and I'm not a metallurgist. I'm not trying to take a deep dive here. In fact, I'll go pretty quick. But you can take a look at the grain structure of what we're getting out of the laser-based and EBM process and compare that to wrought, and you see a fine grain structure. It's a big part of the reason why we have such great properties. Note how, and the chart's a little off here, but note how you can see the ASTM average properties and how the direct metal laser melting compares to wrought, both in the vertical bar and the horizontal bar test case. Now, I only have yield strength, ultimate tensile, elongation, and hardness up here. So I don't have a key missing test, and that is the fatigue test. There's a reason I don't show high cycle and low cycle fatigue, and that's because it does get a bit of a debit, and that is due to the surface finish that you have on internal passages. So, of course, one of the advantages of the additive technologies is you can make these really complex parts. You saw a few of those. Our fuel nozzle is a classic example of how we have this very complex internal geometry. So that's great, but it's not so great that I have a rough surface finish on the inside. That does give me that fatigue debit. So you would see that lower than ASTM standards in this case, and it would not meet the wrought type of lifing. However, the beauty of additive is you can design around that in many cases until we come up with some really good solutions on how to finish internal passages. External's not a problem. It's the internal, usually it's an issue. All right, this is Ti 6.4, similar kind of graphs and similar eye chart in some ways. And once again, you'll see how I've now included EBM. I've got laser-based and DMLM technology represented. And once again, the grain structure looking very similar to what a wrought grain structure. So, you know, we have varying degrees of how close to wrought we get, but I would say, again, very broad brush, we certainly get better than cast, and you can understand the benefits that could bring. So let's switch gears, talk a little bit about what we're doing at GE. So the first thing at GE Aviation in particular, first thing I would tell you is we have a number of machines that we work with. So on the polymer side, we've got SLA, we've got FDM, we've got the PolyJet technology. And on the metal side, we have 5 different modalities we work with at our aviation site. So we have manufacturers of equipment, EOS, SLM, Concept Laser, Phoenix, and the RCAM technology. When GE bought Morris Technologies and RQM, we predominantly had the EOS technology, and we had a couple different generations of machines. We had about 20 of the metal machines when they purchased us, so we still have predominantly the EOS technology. But we're very interested in trying to understand what are the nuances between these technologies. I mean, seemingly, you would think you would get the same output from a machine that has a similar laser, it operates in a very similar way, very similar powder size and morphology that you use. So why would the output be different? It is, not dramatically, but it does have differences. And we're trying to understand what are some of those little nuances, I guess you could say, between the technologies. And I suspect some of it's the software, how the laser is driven, where the laser jumps around on the platform. But there are probably a few other hardware reasons as well. We also have on the polymer side, I mentioned we use Ultem, that's through our Fortis FDM machine. And we do use the SLA and the PolyJet for some cold type test models, as well as mock-ups, and then also a lot of fixturing. So we've been able to find a number of applications. We're very interested as we move forward. There's some interesting work being done on some of the polymer type machines where they're incorporating carbon fiber. So we're looking at some composite type applications with additive, which is becoming very interesting. In fact, in Cincinnati, there's a company that worked with Oak Ridge National Labs. The company in Cincinnati is called Cincinnati Inc. They are known for their large fabrication production-oriented equipment. They've married up to create what they call BAM, a big area additive manufacturing machine, I think. It's very big, size probably of this stage, and it can lay a lot of material down very quickly. So they use an ABS with a carbon fiber impregnated into that. And they're having some very good success making big parts that are near net and that are composite. So we'll start to see more of that in the future, I think. All right, so we talk a lot about the machines. And they are the heart of what we typically think about when we think about additive. But historically, as Morris Technologies and as aviation, we recognize there is a lot on the back end after the parts come back from thermal treatment that you have to be very proficient at. So let me say that differently. If you don't have machining capabilities and you're jumping into the additive metal game, you will find it exceedingly difficult to play in that game. You have to have very competent and good capability on the back end, whether that's EDM, whether that is CNC machining, whether that's special processes like extrude hone or laser scanning, or even special finishing processes. You have to have the full capability. If you don't, then you will have a rough time getting parts turned quickly. And then a couple of things around our prep, industrialization, and production prep. So we have our machines typically live in a controlled environment, not a clean room, but a controlled environment. We have capability on the thermal processing. We also have capability when it comes to powder size analysis. And I will tell you that the morphology and the particle size do matter greatly in these technologies. And so monitoring the health of your machine, monitoring the health of your feedstock, all of those things become very important as you think about going into production. So we have been there, we are on that journey, and it's very interesting to see all the differences between prototyping and production. And there are a number of them, and a number of things that have to be T's crossed and I's dotted. All right, so I think we know hopefully a lot of the advantages of additive. So one of them clearly is a huge time savings. The ability to take that schedule that we all have for producing components on a project and moving some of that back to the left. That becomes a cost savings too. But on numerous occasions, we have been able to demonstrate we can take things that were going to take weeks or even months and reduce that down into the days or weeks. In fact, a couple of great examples. Now, I'll preface the high pressure turbine blade photo and thing I'm going to say here is that we are not producing production high pressure turbine blades additively. High pressure turbine blades typically are produced as a single crystal casting. They have very, very extreme environments that they live in, and to date we have not seen additive be able to live in that environment for high pressure turbine blades. There are other parts of the engine, low pressure turbine blades and other things that might be a good fit, but not high pressure. However, for test purposes, where we only need to get roughly 300 hours of testing in order to get the data that we want, high pressure turbine blades produced additively is a huge cost and time saver. So we can take what normally would be a 12-month cycle to produce those blades and squeeze that down to potentially about 3 months. So that's really a huge time saver. And then, of course, we can produce parts that have high complexity to them, like our fuel swirler there for our power and water cousins, or a combustion component. So we use the technology internally at Aviation quite heavily for our new product introduction or our prototype hardware. That's a big application of how we use it. But we're not stopping there. In fact, when we look at an engine, we look at a lot of different areas of that engine where potentially the technology can be used. So I won't go into all the different items that are on our docket of things we're looking at and that we think will be the next product that will make it to production. But these are areas in the engine that I think are worth looking at for additive. And they range from the compressor area to the combustion, some of our structures, certainly externals, although not HPT blades, but LPT blades potentially, and various installations. So a lot of areas in the engine are great candidates for additive. And we are exploring, as others who are involved in this business, explore and look at the different components. But one of the best applications, I think, of additive isn't just, again, taking that part that you might cast or that you might create some other way. One of the great applications of the technology is trying to look and say, if I have 5 or 6 different parts that I currently machine or that I cast and I weld and I braze and I make that assembly, can I go from that and make the whole assembly as one part grown? And there is a lot of capability for the technology around that particular front. And of course, the optimized structures is something that we look at. So if we can drive even a pound out of a component, we look pretty hard at that because that has substantial benefit to our customers in weight savings, thus fuel savings, and thus cost savings across the fleet for the lifetime of that engine. And you're talking about very long lifetime engines, 20, 30 years that these engines are in service. So reducing the weight is a very big driver of why this technology makes a lot of sense, not just for us, but for our customers. So let's talk about the fuel nozzle. This has been relatively well publicized at this point. It's a story, it's a great story, and it's been a very big success so far, and we're just on the verge of taking that into production. So the fuel nozzle obviously comes out of the combustion area. For our LEAP 56, which is our next generation LEAP engine, the bread and butter product of GE and CFM, frankly. The LEAP engine has 19 fuel nozzles. Each engine has 19 fuel nozzles. Now, we're in the neighborhood of around 7,000 engines that have been sold. We're ramping up across the entire supply chain and entire organization to start to produce these engines. These engines have composites on them. They have CMCs on them. They have a lot of advanced manufacturing in various ways that are embedded in this engine. It's a phenomenal engine. It is a technological marvel, and it's very exciting that additive will be at the heart of the engine in the fuel nozzle, delivering the fuel into the engine. So you have a picture of the additive fuel nozzle there, and as I said, there's 19 of these. That means when we hit full production, we're going to have to produce 40,000 of these nozzles a year. So that's not automotive quantity, but for the aerospace industry, that's pretty good quantity. And the complexity and the criticality of this component in the engine, that's really a huge undertaking. So why did we go down this road? Why did we even consider taking additive and leveraging it into one of these most critical components and taking this huge swing that GE Aviation has taken? Because it is that. First part, really, that's going to be in a production engine is the fuel nozzle. It's not a mundane bracket. It's not some other component that it doesn't have a lot of criticality. This is a very critical component. So there's a convincing reason. One of them is that we were able to take what was 20 pieces, cast pieces that were machined, cast, welded, brazed. We took that paradigm of design, and we had some really talented designers and engineers that reconfigured that for additive. And they got that down to one part that we're going to grow. And it is an absolutely phenomenal and very almost artistic design on the inside. It's very elegant. And we have snaking passages going all over the place. Because of that, we have the ability to treat this like as that bullet point says, a very efficient heat exchanger. And that heat exchanger effect gives us higher durability. We're estimating a roughly 5 times durability. Well, that matters because that means that's less time off wing and our customers have to endure. So so there are a lot of cost reasons and performance reasons why we went down that path. Compared to our previous generation fuel nozzle that was on our GE&X engine, we see a 25% weight savings in addition. So once again, a huge benefit being able to reduce the weight of each of those fuel nozzles, multiply it by 19, and you've got a significant win. So, as I mentioned, we're in the process of ramping. That says around 6,600 LEAP engines. I think we're getting close to 7,000 at this point. With entry into service in 2016, we're at 2014, and we have a lot of things in motion right now. So we do have our facility picked. We have started to place our orders for the production machines. And we have all the other surrounding items that come along with producing a component. So the quality side of it becomes very, very critical and important, of course. So how do we inspect these parts? What kind of speed can we inspect them with? So we're not only looking at these things, we're well on the path and well on the way to having these installed and ready to go. That's not a 6-month journey. That is a good 5-year plus journey with all the other items. The testing of the materials, the testing of the components, that's been a 10-year journey. So I will say right now that, we tend to think about this technology. The media does a good job of this. In the last year and a half, 2 years, we see a lot of activity in the media talking about additive, and it can do anything and everything, right? Everyone's going out of business unless you're an additive. So, the technology is such that it really is based on some fundamental things that, at least for GE Aviation, we've been doing for over 25 years. So we're talking about metal powder, metallurgy. We're talking about lasers. We're talking about CAD. These things have been around for a long time. We're just putting those three things together, and we're controlling them a little bit differently. But we have deep experience in powder metallurgy. We have deep experience in laser processing. We've been doing repairs for again, over 25 years using lasers and powder. So this technology itself, using machines that I showed you before, we've been doing for over 10 years. So through that process of period of time, a lot of it's been kept quiet, admittedly. GE didn't talk about this for quite some time. But for 10 years now, over 10 years, we've been going through and really qualifying the process, understanding what our upper and lower limits are, understanding where the failure modes are for these machines when you're ramping up to full production. So that's why I say when we're headed into production, this didn't just happen last year. This is something that's been coming for quite some time. Now, before we start the video, I just want to quickly let you know that I'm really excited to be able to show you this. This is the first time that I've been able to show you how we make our fuel nozzles. So you get a sneak peek at how we do this at GE Aviation. So if you can go ahead and roll the video. This does have sound. First part is it. Do we have sound on that?
To be made. And making something stronger will mean making it lighter. One day, factories will work with the cloud. One day is today.
So there it is. That's how we make our fuel nozzles. They drop right from the cloud. All right, I work in the wrong department. I got to work in the marketing department. Those guys have way too much fun. I think they're based in Colorado. So yeah, so that's fun, right? But it kind of does us a bit of a disservice because I think certifying agencies look at that and have a heart attack, and and then we have some explaining to do. But anyway, it's neat to see that happen. Well, I'm going to go on to a little different type of thing, and this is again back to the media. How many, just out of curiosity, if you don't mind raising your hand, how many saw a YouTube video or heard about somebody who made a actual gun you could fire out of additive? Yeah, a fair number of you guys. So okay, that was great, and that was nice to do that, and I think it does demonstrate capability of the technology. It really sort of had a big firestorm of blowback because people were all afraid now that you could additively produce your gun and it was going to be a big security threat. So, that's going to happen. You can't blame the technology. That's going to happen. People, you can make a gun with a mill and a lathe in your house, so it's just 3D. But still, we wanted a more positive message out there, so we're working on this message. I don't have the exact video, so you're going to have to really bear with me when I pull the video up in a few slides here. It's kind of grainy. It isn't exactly what I want. But let me just quickly go through this. So we decided we're going to make what we call an angel trumpet engine. So this is a small little engine. You'll get the scale when I show a couple of the videos. So here's the sequence. We took some files off the web, bought some plans for a little model aircraft engine, and we modified them for additive. So we did our little CAD work. We sent it to the machine. You can see some of the photos up here that are the parts building. Then after build, we did our thermal processing. We pulled them back. We put them into our CNC machining to get the right tolerances. After that, we did some hand benching. So we cleaned up some parts. It was only a few pieces. So we have this gentleman, Dave here, who is an extremely talented guy, and he was able to do the hand benching, get us to a nice looking component. And here's what the final parts look like. Every part of this engine was additively produced with the exception of the shaft and the bearings. Those two were not. But everything else was additively produced. You can see all those components on the table. They were post-machined, they were post-thermal processed, and they were made out of cobalt chrome material. We then assembled it. So here you can see the sequence of events as we start to assemble the little engine components together. We added a little tube that was also not additively produced for the fuel injection. And that's our little angel trumpet component. So you'll have to bear, if we can start this video, this also has some sound, and if you'll just bear with me for 2 minutes, I'm going to show you what this little guy looks like as it went into one of our test cells. So this is actually one of our test cells at GE. Again, I apologize for the quality of the video. When we get to our real test, we'll have much better quality. But what I want to show you is that we went ahead and lit this thing off. Now, they're not in the room, but somewhere in the background you're going to hear some voices. So we'll go ahead and listen to this for a second. Exactly here, but I think he said 5, and I hear 8. He's talking about RPMs, so you hear it. That's what they're talking about. 12,000 RPM. 14. That's when the bearings blew. They burned up. So some of you are probably like, okay, I'm waiting to see this thing blow up into 1,000 pieces or something. So the good news, it didn't. So, that's what we're going to do is we're going to put this little video together. It's going to have all those photos that you saw and how we went about the whole process posted on YouTube. But we'll have things like how much thrust are we getting and what temperatures did we get up to. So we've got it all wired up. It should be pretty cool. I was hoping to have it for today, but unfortunately, they had to redo the bearings and a couple other things. But that got up to, I think, 33,000 RPM. And I cut the video, the sound at the very tail end because there was a bunch of hooting and hollering going on in the background, and I figured you probably didn't want to hear all that. So, but that was our neat little test of an engine. So I thought that was kind of fun. So look, great technology, a lot of fun stuff in the technology, but there are challenges too. And we've learned a huge amount over the course of time that we've been playing with the technology. So, how you orient the part, what kind of stock do you add to the part, where do you add support structures? So these are all things that you have to know when you work with this technology. You can nest multiple parts on a build platform. That can affect the build and the quality of the parts. You have to be aware of what all that is. There are some things that happen that you just need to be aware of. For instance, you get a witness line on that rake when you have a power outage. Why does that happen? Can you still use that part? That happened because of a power outage. The machine was down for probably 8 hours until we came back in. It happened in the middle of the night. But what you end up having is when you restart the machine, you have metal shrink and you start centering on your next layer and you have this witness line. So we did do some testing and we felt pretty confident with the right restart procedures you can keep going. However, we would never do that for a critical component, and we would always have to get the permission of the engineer and designer that we were about to do that, which in essence meant we started over. So the other thing that you'll get is small holes. You'll tend to get horizontal holes built horizontally, so the layering going this way and the hole this way. You'll get little stalactites coming down from the top, and that's because the laser picks up in the case of the laser-based processes, you pick up a little bit of the particle underneath and you don't have a supporting layer underneath it. So those are some close-ups of some parts. They're not perfectly round holes. They tend to have a little bit of goobers up there at the top. You can have thick parts that pull up from the platform, and knowing how to really anchor those down becomes important. Knowing what kind of stock you need to add so that you have enough stock to post-machine to get to your tolerances. Those are all elements of the nuances of the technology. We had mentioned before in the video, I talked about the cake of parts. Here's a good example of pulling it out of the machine. We bead blast away to expose the parts. Once again, a nuance of EBM is you have a really tough time, if it's even possible, to get internal material passages, material stock and internal passages out. You have to do that in a mechanical form. So there are a lot of other challenges. We have challenges around surface finish and material properties, rapid qualification, something we talk about a lot, and our universities and our government friends are helping on that. Inspection is another big area. That can be up to 25% of the cost of a production part. In-process control and some other items like that. So we're doing a lot of activity at GE Research and at GE as a whole, at Aviation and with some of our partners. So we're looking at process modeling. We're looking at things about how can we take physics-based modeling and apply it into additive, and how do the models look? I mean, this is very, very computer and memory intensive type of processes. Distortion compensation would be great. Wouldn't it be nice to know when you get your model, you can predict what the distortion is and what you need to do to anticipate what that distortion might be on the front end, so that the first time you build it, you have a good part coming out. So distortion prediction and mitigation is another topical area that we're working with. There's some topics we're working with America Makes, not far from here, and we're working with labs like Lawrence Livermore National Labs out in California and some other folks. So basically, this is really interesting work. Again, it's not easy. There are a number of parameters that come into play: what laser power, what layer thickness, what materials are you working with. So there's a number of different things that are taking place. And again, understanding just the process physics is very, very difficult. It's work we're doing. It doesn't stop us from going forward with how we're working with our parts. This hopefully will make us more efficient as we move forward in the future. And then basically trying to predict, again, in real time, feedback loops and what our stresses are, et cetera. So a lot of work being done with a number of different people, consortiums, collaborations, government, academia, and industry. And there are a lot of people globally, as well as in the United States, that are working on these problems. So a couple of additional considerations. Where are we heading? Well, quickly going through this, adoption is clearly accelerating. We're seeing more and more companies realize this is a disruptive technology for their businesses or for their components they make. We have a huge, really neat future coming at us with multiple technology advancements. So what does that mean? Does that mean our supply chain is going to disappear? If you cast parts, if you machine parts, and are we going to see rooms that look like the room that's out of our additive development center here? We have banks of machines that are just producing parts. So my short answer is no, not in our lifetimes. You will be fine if you're casting parts, and you will use cast parts and machine parts and fabricated parts. But you probably will also start to hear and use additive. And yes, we will see production facilities that look like that room, where you have a few people walking around starting builds and taking parts out. You don't have banks of machines with an operator at every machine. So I think there's a shift, but it's not going to be a dramatic shift whereby we see entire industries disappear. I do think we have the opportunity to take additive more local. If you're in the oil and gas industry and you're out in some remote location, wouldn't it be great to drop a pod down, and instead of waiting for that replacement part, you can grow the part? If you're the military and you're in the Navy and you have 2 ships that sail with you on your fleet that have nothing but spare parts on them, wouldn't that be great to eliminate one of those and just have machines instead in the other ship that can produce a lot of your spare parts? Not all, but a lot of them. You save billions of dollars if you do that. And for us in the commercial world, parts inventory, it would be wonderful to see a reduction in that. So think about smart planes and smart feedback systems where you know that you have a part that's about to fail. And when the plane lands, let's say you're able to quickly put a replacement part on that you grew while it was en route. Okay, that's a little science fiction, a little far out, but the concept being instead of carrying loads of inventory, maybe we can have depots that actually have machines that can produce the parts on demand as needed from digital files. So a lot of work being done on that front as well. Broad trends, we see obviously increased acceptance and adoption of the technology. We're seeing a ton of new business models out there. It's really interesting to see how people think about using and leveraging the technology. I do see a challenging IP landscape. There tends to be, excuse me, on technologies like this, a land grab for people just throwing out patents to try to stake out their claims, whether they have things or not. And that can be a bit problematic and hold us back some. But, you know, I think we're starting to see all of these trends. I think also consolidation in the industry, of which Morris Technologies RQM is a good example. But if you look at our industry, you see a number of companies that have been acquired by larger companies, either in the additive space or OEMs looking to do the same. So that creates opportunity. It also creates some challenges. I think we're still relatively in the early phase of adoption. It's starting to move into that primary majority realm, and I think we're getting there sooner than later probably. And I think the technology itself is still early on. So look for tremendous advancements in all the technologies, whether they're polymer, metal. Look for 3 times the throughput that we get today in 5 years. Maybe 10 years, you'll see 10 times the throughput. All that does is it takes the realm of possibility of parts and it grows it exponentially from this to this every time you take it up 1x on the speed and throughput. So if we look at the total global manufacturing output, roughly 11 trillion in the world globally. How much does our little industry play? It's that little dot that just showed up. And if you look at that, that's roughly 2.2 billion, call it 3 billion even today maybe. So 3 billion is our little industry, which is 0.03%, 0.02 to 0.03% of total global manufacturing output. So my question is, what happens if it was 1%? If we had 1% as additive and total global manufacturing output, we would be at a $100 billion industry. That's why the valuations of some of these public companies have risen so high. They kind of fluctuate, go up and down, but that's the potential. So we're a teeny industry. We're $3 billion as an industry, but I don't think in the terribly distant future you can envision a $100 billion industry. So finally, I want to leave you with one last video from our marketing folks, and you may have seen this commercial. It's been playing more and more. They even have a shortened version. They keep the key part of that video in here. So let's go ahead and play that final video, and this should have sound too.
My mom, she makes underwater fans that are powered by the moon. My mom makes airplane engines that can talk. My mom makes hospitals you can hold in your hand. My mom can print amazing things right from her computer. My mom makes trains that are friends with trees. My mom works at GE.
All right, so you caught that part about the engine. Again, that's how we make engines at GE Aviation. They just all fly together and come and boom, we got it. So, you know, I don't know what the problem is trying to make 7,000 air engines in a short period of time. Like I said, I should have been working for the marketing team. But once again, that's a national commercial. And my point more on that commercial was the little girl says, my mom can print amazing things right from her computer as they show the engine coming together. So, you know, when a company like GE is starting to put out these big marketing campaigns, even though they might be a little bit futuristic, I think the point is it's mainstream, it's real, and we certainly believe it is an enabling technology that we expect to see many components on our future aircraft engines. And I would expect to see many of that and the kind of components that you guys are starting to produce as well. So I just want to thank you very much for the time this morning. I don't know if we have time for questions or not, but okay, couple questions if anybody has them. And I think you need to come up to the mic if you want to have a question. Yes, sir, but if you can come up to the mic, that'd be great.
Yeah, I do have a couple of questions. One is, you showed the turbine blades, and if you were to coat them, can you still make a coated turbine blade, or would that break at the bond? And
I'm sorry, I'm not totally understanding.
You showed turbine blades that you can make with additive manufacturing.
Right, the high pressure turbine blades?
Yeah, so my question is a more general question. If you were talking about coated components where you have two different materials
Oh.
coming together.
Right.
Is that possible, or is it going to break at the bonds? Is the bonding
Yeah.
an issue?
Yeah, so it's a great question. So gradiated materials, right?
Yeah.
So at the root, you might want one material. In the middle of it, you might want a different one. And at the tip, you might want something that's abrasion resistant, and et cetera, et cetera. So the short answer is that can be done today in limited ways. So the lens process, for instance, where you flow powder into a laser stream, you can flow different materials. You can go from one material and then gradiate into another material. As long as the material, there are materials that will bond just fine and that you get a good mechanical bond. I'm sure there are materials that will not work very well. We have also done and demonstrated where you have one layer, it's one material, and then we start with a different material and build from that point up. And we've had very good success in the couple of trials that we've done, going from, say, an Inco 625 to another material. And that's worked very well with a perfectly good metallurgical bond. So it is possible, it's just limited in the capability that it has to do those things today.
Yeah, my second question relates to ceramic matrix composites. Do you see an ability to act, because a lot of them are woven structures, do you see an ability to actually use additive manufacturing to make the weaves and build it up that way into a component?
It's a great question. Fortunately, I'm not a CMC guy, so I can beg off on trying to answer that in any depth. But look, it is a layering process, right, in some ways,
Yeah.
as are other composites. So can we automate that process? I don't know. I think it would be great if we could. You can get, consistency and a lot of other things that can be a little bit bedeviling when you're making some of these very complex, high technology type of components. But I'm not expert enough in CMCs to be able to comment on it. And even so, I think it's going to be quite some time before those type of capabilities come out.
Yeah, okay.
If they can.
Yeah, thank you.
Yeah, last question probably, because I think we're short on time. Okay.
Yeah, could you touch on what do you think the major obstacles, and when do you think will be a significant part of manufacturing?
I think one of the biggest obstacles are for parts to buy their way on in a variety of ways. So if you're trying to work with a new material, first you have to understand what are the mechanical characteristics of that material. So that's expensive. It takes a lot of time. It's very expensive. So that's a barrier. Even if you thought that the technology was cost effective in its throughput and efficiency, you still have to overcome that hurdle. Let's say you overcome that hurdle. I think the next one is just the machine's throughput. It's still a very expensive technology, and the circle of applications are relatively small. So if we can accelerate the throughput, if we can build machines, and I say we, globally to the OEMs that make the machines, but if we can get the throughput tomorrow, if it were 10x, you would have many, many more industries jumping in to use the technology, because then parts are buying their way onto their product. Right now, it takes a relatively hefty investment to figure out which ones are going to buy their way on, and it's really an investment in the future. Although I will say for the field nozzle, I believe that bought its way on for a variety of reasons, but for other industries, you're going to have to see the throughput dramatically increase in order to be competitive. It's a broad brush statement, but throughput of the machines, thus cost of the technology, needs to come down relatively significantly. I think 5 years, we'll see great leaps. In 10 years and 20 years, this will be used in a number of applications. This additive technology will be used in a number of applications that today probably aren't being considered. So once again, thank you very much for your attention and time, and enjoy the rest of the day.